Okay, so now we're kind of set up to at least to try to tackle section 18.5, which is the stochastic version, and we're going to have the IID case. And okay, so I'm going to ask you to read this and then I'm going to point you to some. I'm going to point you to some interpretive sections which may or may not help you to the best Lars Lundquist and I can do to wrestle with this question about the intuition that drives this result. So with an uncertain with risky endowments, we've set this up, and we're going to have IID, and I wrote the Bellman equation. The first order optimum conditions for that maximum problem are going to be this restriction. So we're going to have no borrowing constraint. Beta R, pi s, and then we have v prime, kind of a standard R, a minus c plus ys bar. That's our Euler equation with equality if non-negativity constraint on savings is not binding. And so this equation, I'll let you look at the technicalities. This can be translated to this. Because we've assumed beta R is equal to 1. This can be this implies this. Next period. So this implies that v prime a t, I'll just write this, is a super martingale. It's greater than or equal to et v prime at plus 1. And v looks like u. So the gradient of the value function is a sub-martingale. That's what this says. This is a sub-martingale. So what this means is that so there's a theorem of Doob. It's cited in the appendix. What it says is that v prime of a must converge almost surely to a non-trivial random variable. You may be studying this in a econometrics class because a submartingale convergence theorem is used to prove consistency of various econometric estimators. But this is a bounded submartingale. And so in general, it converges to a non-trivial random variable, but because of our special cases, the way we've set this up, except I warn you that in a particular exercise, I've changed the assumptions about IID-ness, and it's going to make it a non-trivial random variable. That's just a side. So what has to be true is v prime is greater than or equal to 0, so it's bounded. So what's going to have to happen to us is v prime of a t is going to have to converge to 0 almost surely. But what that means is that implies that at is going to diverge to plus infinity, and that consumption is going to diverge to plus infinity almost surely. So this is all following from our restrictions. This follows from u prime being positive and this being negative. So we want this to be positive everywhere. So it can't be like quadratic utility. It can wiggle around. My marginal utility can wiggle around, but it cannot go negative. I'm not imposing that I'm not imposing this. Globally, but there's a sense in which if I impose this globally, I could have gotten all this pretty easily, like the footnote that we talked about in chapter 3. Still mysterious, but that's what happened. Here we're not imposing this, but it's happening nevertheless. So there's a no borrowing constraint. There's a risky endowment. There's a risky endowment. There's a risk-free asset that the person can hold. And what the person is doing here is the consumer is self-insuring. If we let there be, we already know if we let there be borrowing if there was no borrowing limit, if there was a quote unquote natural borrowing limits, under this condition, under our circumstances, the person would be able to consumption smooth. The person cannot consumption smooth. So instead what he does is he moves the consumption, he sends the consumption north. Okay. So so here's some hints about how to think about what's going on here. The quote unquote intuition. Some of the intuition at the top of page 817. There's some analogies to what was constructed, what was done in the non-stochastic case. In the non-stochastic case, we also saw that there was a force pushing the endowment, the assets up, and consumption up. Here, so it's a little bit, it's more subtle. So there's a section 18.7 called intuition. Intuition. And that's that intuition, I think, is somewhat related to the nature of this graph. And but I'll let you read that if you want. I personally don't really care if you think you have intuition about this. The mathematical analysis and the submartingale convergence, that's something that's useful and that will reappear. Okay, I wanna conclude this discussion because this with a couple of remarks. This self-insurance motive often appears, like in lots of setups like that people like Mark Gertler, Bernanke, Kiyotaki put together, where there are financial frictions of various kinds that give rise to indirect utility functions that are concave. It sets up a motive to for people to inside the model for people to get out from under the restriction by doing self-insurance, by accumulating enough assets to render the restriction not binding. I'm just going to put that on the table because if you do finance or macro or public finance, you'll see that over and over again. So this force that we've been isolating here shows up through the back door in other models. Okay. And people are interested in shutting down this force. So to weaken the force, I want to mention two things. One is something that you're going to see in so-called Bewley models. So there, to weaken the force, R beta equals 1 was a key thing in allowing the force to operate. And essentially what Truman Bewley's idea and Iagari's idea and Huggett's idea that you'll often see in what people call Bewley models, it's to lower the interest rate so R beta is less than 1. And what that does is it changes this marginal condition directly, and it directly kills this martingale submartingale result because that, and that is done. We'll talk about this more later, and it's discussed in when people talk about Iagari models. That is done in order to allow assets to converge to a stationary distribution. See, here's what's going on here is assets are diverging. But Bewley models live on having a stationary distribution. So they're going to do something to kill this by forcing the interest rate down. That's one thing. Here's another thing to weaken the force. And this is talked about at the end of the chapter. And what that is and this big contribution to this was made by a fine NYU graduate student, Zhenghao Zhu, in a 2020 paper. Building on work by Marcet, extending work by Marcet and others, Obiols Holmes. What they add is endogenous labor supply and endogenous labor income, and therefore endogenous labor income. Because one way you can self-insure is, well, you can change your, you have an effect on the risks in the labor process that you earn. And in this model that we've been talking about with exogenous endowment, you can't do that. But in section 18.8, you could sketch it. Things are changed so that the utility function now is consumption and let's say time that you have, leisure, and you can reduce your leisure and you can work more, and that'll affect how much income you get, and you can manage your that changes the self-insurance motives, and it can lead assets to converge. So that was another way that forces have been weakened. But this force that Chamberlain and Wilson analyzed so beautifully is going to be present all over the place. So